Hi, everyone. Welcome to another episode of the Haskell Study Group. I'm your host, Ron Baden with Atlanta Functional Programming. For those of you who joined us yesterday for our Common List Study Group, thank you for joining us this Thursday evening. Today, we're going to be discussing testing in Haskell. Obviously, a very important topic when you are going to be designing large-scale software systems and even libraries that you may want other people to reuse at some point. The libraries that we're going to be covering today are the HSpec library, a library that allow you to write specification-based testing libraries. Tests in a unit, as well as the QuickCheck library, which is probably the more popular Haskell testing library that most folks are aware of. This library does something called property-based testing, an approach that was actually pioneered directly in Haskell and leverages the full capabilities of the actual type system to actually write out its properties tests, and it will use that information to come up with random inputs to whatever function APIs that we are testing. To begin with, we're going to just quickly go over just some brief things about testing, just some of my experiences and the importance of testing. Obviously, some of this is more or less probably stuff that most of you already know, but I thought I'd at least briefly mention it anyway, especially if you're coming into testing and you're wondering why we're not talking about unit tests or X unit type of tests. Um, so we're going to begin with that and talk about the differences between what spec-based testing is versus real unit testing using something like, say, HUnit that is also available. And we won't be discussing HUnit today because the HUnit API is more or less the XUnit API that most people are familiar with. It's a series of assertions that you can actually use inside your test cases and actually write out your tests in that manner. Spec-based testing obviously takes a little bit of a different approach than unit testing, and it's something that if you're not familiar with the approach, obviously it's going to be a little jarring, a little different. After that, we will go and test and talk about quick check and property-based testing and what the differences are from unit-based testing and spec-based testing, and go through a couple of simple examples from this. I decided just for time that it may not be given time permitting, we might go through a couple of examples that I thought were pretty neat in the book to actually go and bring some of these concepts home. But of course, if there are topics or questions that people have while I'm running the stream, by all means, go ahead and post your question in the chat window, and I will answer it you know as it comes up. To begin with, we're going to first start about talking about a little bit about testing, and then we'll be touching base with this example that I have this kind of set up. Uh, Mainly because of the fact that I'd like us to kind of like just talk through some of these ideas that are available inside Haskell or general software engineering in general that is usually discussed when you are talking about testing, like what is a system under test, what is the unit that you're the atomic unit that you're dealing with, and so forth, and where does the testing frameworks kind of lie. All right. Um, to begin with, we have, and I'll just use this buffer as my example. Although this is going to be a Cabal file that will hold this, and I will post these notes, if you will, inside of our GitHub repository um, uh, later this weekend once I have all the stuff like cleaned up for you guys. But to begin with, let's talk about testing in general. Everyone knows that Haskell, one of its selling points is the fact that when you compile your code, usually it is type correct. And it is one of the big reasons most people try to emphasize, oh, just design your types. And as long as your types are actually designed You have a good way of knowing that your code is well formed because the compiler will throw a compiler error because the type constructor kind of failed to construct a type due to some invalid condition that it's seen at compile time, and so your code will just never get generated and your executables never get built. Now, for the majority of what I would consider basic errors, mostly related to type design. This actually prevents a lot of those errors. But as we all know from real world engineering, it doesn't prevent every damn error that's in existence. It doesn't prevent some code that may be well typed but doesn't perform as expected in with respect to requirements that a particular customer may have with respect to um, particular features that should exist but don't necessarily have not yet been implemented. Even in the case, well-typed code could also include API calls that are either non-existent or their input-output contracts don't match the contract that was agreed upon by maybe say a customer or and the developer who developed it. This is where testing kind of comes in. Testing usually is with respect to this kind of contract that you're actually going to be dealing with. And it comes in many forms. Most of us are familiar with the standard unit testing framework approach, where you have a class or object or even function that you're trying to test. You know what its basic inputs and outputs are, and you go ahead and you define um, uh, your test using those proper inputs and outputs and make sure that the expected outputs are coming out of for the given expected inputs. This is kind of the basic level of unit testing that most people are familiar with. Okay, we are testing solid units of software independent of each other. We are looking at the call graph or even the actual control flow graph to figure out what particular aspects of the control flow we'd want to test to make sure we cover as many cases as possible and test as many sections of the code that we built. And this encourages the obviously the ability to then see whether or not a particular function is taking on multiple responsibilities, giving us an opportunity to potentially refactor it, make it into smaller, more indivisible, more atomic units to actually go in and make sure that they get tested so we have better code quality, better code coverage, and so forth. Usually, when you're talking about testing, you are dealing with this kind of level of unit testing. Okay, so in I'm just going to briefly mention it again. We're not going to be covering this library, but it is available in Haskell. You have this approach in testing using HUnit. HUnit is a unit testing library that follows the XUnit approach to unit testing. So if you're first getting into unit testing and you want something that's more familiar and HSpec is not that we're covering today in the book is not up your alley, then by all means go for actually at the very least coming up with something that's simple and HUnit is at your disposal. I'm just mentioning that we're not going to be covering it today, but it is available for you to do it. And its API is very similar to actually go and write your code. All right. Spec-based testing compared to unit-based testing is slightly different in that it's actually takes on its inspiration from the BDD movement. Now, for those of you who know about this movement, it was a very you know uh, English kind of like inspire it's a type of testing that basically describes the behaviors that you're defining, all right? You are still actually in unit testing, testing specific functions, but um the difference is you need to write your test in terms of the actual assertions that are in some sort of human readable language. This actually encourages now you to write your assertions in a way that non-programmers can probably understand, because they may need to actually read and interpret the results of the tests, and rather than probably creating a separate set of analytic tools that actually extracts the XUnit tests and presents them in a way that your non-programmers can understand, your managers, project managers, product managers, and so forth, you can actually use the output from spec-based testing to actually hand it to them and give that test report as a way of at least encouraging them and giving them confidence that the code that you're writing actually is meeting to their specs. Um, so a lot of this test follows kind of like, in most situations, it's going to be following like something like the given one den syntax that you may have encountered in BDD tools. But the more recent spec-based testing frameworks, and again, they're like unit testing, but the assertions are written in human readable format. Um, the one thing that you should be aware of spec-based testing is in terms of Haskell, a lot of it is going to be written in such a way that we are still leveraging um, most of, if not all of, the Haskell type system, as well as function composition. We'll see that to write out our test suite. Okay. Um, the first library that we're gonna be covering is essentially the spec-based testing library. Like I said, we will be touching base on property-based testing, but I thought, it would be easier, unlike in the book that covers kind of spec-based testing versus property-based testing and then going straight into the code. I thought it would be easier for us to first present each concept independently of each other and then do a compare and contrast maybe discussion afterwards. So the spec-based testing library that we're going to be leveraging is something called HSpec. All right. It is a specification library that's available through Cabal. And in order for us to do this, we're going to have to first write out our test. Write out a project and then work our way up. So I have this empty directory here called Edition to build up a library that could be used to actually go and be used to actually define different add functions that you can define. And what we're going to do is we're going to first write a Cabal file, which remember Cabal is our build file for a single module. It's not leveraged to actually write multiple modules in like say stack, but we could certainly write this Cabal file so that it can actually know that uh, that this it's going to build every Haskell file that's available in this particular directory. And it's pretty simple. If you recall from our coverage on build systems, we're going to be having to specify the name. And I'm just going to go ahead and say that it's called edition. We're going to specify the version, which obviously this is just going to be, our first version. This is, remember, major, minor, um, point and patch release. And of course, you have to specify a couple of other things: the license, the author, and the maintainer. License is a license file. Are you going to provide? You need to provide the author of it. You know, in this case, we can just say, my first name, or John Doe. You can, specify your name. Uh, I'll say Joe Program Vatum here, and obviously you have the maintainer. And the maintainer is dart at dartvader.org. You usually need to specify an email address, and this is all metadata that's part of the package that needs to be available. Then obviously you need to specify, what is the type of package that you're building, which is text. What is the build type, When you say simple, you are dealing with essentially a simple build system. It's just going to probably call out Haskell with some compiler warnings. I mean, sorry, with some compiler flags to actually go in and um, build it out. And you need to specify what your Cabal version is, which in this case we're going to be using greater than 110. All right. After that, you need to go and specify important details about the library, and this is defined, if you recall, inside the library section. Okay. This includes what exposed modules. What modules are you exporting from this module of this? And of course, we are exposing the addition module with a capital A this time. We need to specify the GHC options, and these are the options that are going to be directing the compiler on how to actually build our software. And in this case, we're just going to have two command compiler flags turned on, specifically turn on all warnings and make tabs into an error. Is important. And then we have obviously what version of Haskell we're actually building up, and we're saying that we need the base libraries greater than 4.7 and less than 5. I think this is for improvement of the prelude. These are all the library dependencies that you're building in on. And then you need to also specify, in this case, the dependency of the testing library that we're going to be determining on, which is HSpec. Once we do that, then we have to, of course, add two other things: our sources, which is specified by HS sourcers, and we could just do uh, period because we're actually building the module of every file in this directory, and we need to specify what version of Haskell are we actually writing against. So the default language that we're dealing with is going to be Haskell 2010, just because that's at the time the library's the language is written. Now we have this all set up, we can actually go in and actually set up um, our um, our stack project. So here we just do stack init first, you know, set up our stack project. Everything is kind of good. And here, if you actually look at our directory, you see a stack project here. We also need to obviously write out, just so that we can actually build a system, an addition file. So if we go here, go up and go to addition, and we just do edition.hs. Just write this out, and let's see. Oops. Wait, for some reason I am locked up here. So why? Let me. Oh, this looks like it's locked up. Okay, 1 second. Please kill dash 9 vim. Okay, play that up, and we have our stock here. Okay, so let's go ahead and do this again. Delete this swap file. Actually, let me do this before I do anything. Sometimes when you're using Vim, you have to deal with this. For those of you who may be wondering why I am not using Emacs today, I currently have a little bit of a. Oh, sorry, I just mistyped that. I had a bit of mishap with my Emacs configuration, and now my current machine configuration for Emacs does not work the way I expect it to, and as a result, we are kind of having to go and improvise for tonight's episode. So apologies for those who are looking at this saying blasphemy. What are you doing? All right, I like I do use whenever I can. Our good friend Mr. Vim, and I'm a big fan of him. So here we're gonna go ahead and make a hello project with this, and then we're gonna say hello equals print. Oh, sorry, not print. Put string line hello. Simple project just to make sure that everything's kind of like built up. Okay. So the next thing that we could do is of course is why is this getting locked up? 1 second. I accidentally hit some sort of key combination that keeps killing me. Okay. Right. Let's do this one more time. Vimprox DLL. Um, oh, this might be getting screwed up. Okay. Let's do this. Open shell buffer directory. Okay. So here, we have this. Plus. So here we have a basic module. We have our, if we go here and split the window, we have our edition cabal file, which we loaded to as well. And we see this all kind of like set up with our stuff. So now we're kind of available to actually build this thing. So the way we build that, of course, for folks who are familiar with Stack, you set up Stack build. It'll go ahead and grab all the libraries in question. Obviously, in this case, we're also going to be grabbing QuickCheck's latest version. It's going to compile the libraries for your system. So it's going to grab the source code. It's not actually getting some sort of like registered version of it. It's getting the source code for those open source projects, setting it all up, and then build the final executable tab before it actually goes out to build your project. Now, here, as we can see, we have we have built out our sorted things, but it did not actually set up. Okay, let me do a stack init again here. Let me stack YAML dot lock. Okay, stack init again. Okay, matches, blah blah blah. Let's see what it says here. Cabal patches as da, 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 da. Okay. See here, did it build it up? No, it did not. Let's see what stack build does here. It does not actually. It's building our project, which is weird. Give me a second here. I may have actually messed up something. Um, oh, I forgot to touch the license. That's why. Touch license. Now this will build. We have our libraries built up. The license is necessary if even though we're not building up a license right now. But when you're building your libraries, obviously you need to set that up to actually go and uh, um, just so that Cabal, in this case, Cabal was complaining that the license file doesn't exist. Anything that's in the YAML file, it's going to have some issues on. It's kind of assuming that you're going to be building some sort of main um, application of some sort, and it just skips the rest of the things because of the parsing error that it couldn't find the files that you've asked for in the metadata. Now that we have this, we can actually test it. We can actually go into GHCI by using stack GHCI, and you could see that our module actually got loaded. And if we do say hello, we can see that it's hello. We can actually go in actually introspect it and so forth, and it of course works. We haven't actually gone through and tested anything, right? We've only set up the infrastructure now. This is kind of a basic test harness that you just want to have at your disposal once you kind of work through stuff. And again, if you go and look at, I think it's tree is the command. Oh, right, I don't have it installed on here. You can actually go and grab the you can actually get a nice sorry, um, L listing of your projects here, and it's just a few things to actually set up your test harness, your basic test harness. Okay. Now we're gonna actually go in and leverage the HSpec portion of the library, and this is nothing more than a module that's part of the core HSpec. Uh, um, well, it's part of the core testing module that's available. Um, If you do this, it will actually go ahead and set it up so that your library is ready to be tested with HSpec. Now, one thing to recognize is, of course, in our case, we are adding this to the main module. You may at some point obviously create your own edition.test, editiontest.hs. We will do that later to do some little cleanup refactoring as we go through this. But right now, we're just going to keep everything kind of in the same module to simplify things from a building standpoint. One thing to note about imports again that I think we covered when we talked about exporting libraries is that all imports must be at the top of your file. If you go in and attempt, so this will actually build, although we may not be using testing right now, it's going to probably um, complain as you see here. But if we go in and attempt to say print this guy out, put this at the very end and try to localize the imports, you're going to end up seeing something like this as your build error. All right, this is a parse error on input, and that's because of the fact that it's treating import, even though it is a valid keyword, has a function call, and it is and more importantly, it doesn't understand that it's part of the main grammar that you see that doesn't fit well into the way QuickCheck kind of I mean, sorry, the way the Haskell grammar kind of expects you to build out your things. So um So let's go ahead and go back to what we had before. Um, just one moment here. So here, um, let's make sure that we build everything correctly again. All right, good. When we load this library into GHCI, and this is something that's important, you are going to get these warnings, but now you have something very nice and available to you as part of the REPL. All right. You can actually browse what's available inside this library, and we're just going to do that very briefly here. As you know, the book kind of mentions that you can actually go through this. This kind of shows you what you have. It's a pretty big library. There's a bunch of stuff that's around with. We're not going to cover them all, but these are when you browse a particular module, you are getting all the types and top level exported definitions that are available and their full signatures. This is one way of actually interacting with the particular library so that you can actually go and look through, what you can and cannot do inside this particular. For the time being, we're going to be leveraging a particular format for building out our tests, and it's a very simple one. And it's going to be we're leveraging it uh, inside our test module here. All right. The one thing to point out is this test module. We're going to be starting out with something simple here. I will certainly eventually move this over into let's say we do this. Create a lib.hs for the time being. All right. And this is a module lib where you have this, and this is going to be part of the same module that we're going to be having inside of our tests. Of course, this is not going to be the full things. At some point, we're going to have to expose this as part of the expose modules if we want to say ship it. But for the time being, we're just going to keep this in a local area. Um, and what we're going to do is we're going to use edition.hs to being our test for the time being. All right. Our most tests will have a main function that will contain, that's a IO monad. And to write an HSpec test, you have to basically leverage do syntax composed with HSpec. So what you have is you start HSpec here. If we and HSpec is nothing more than, as you see here, a spec that will take in a specification and then return an IO monad. All right. Specifications are actually typically written with either it or other ways of describing it. And we'll go through some of the other, I think we'll just touch base on it in a couple of examples to actually allow us to leverage some of the bits and pieces of this library so that you can actually go in and, write out your main pieces here to write out the spec. Okay. Every time you build it, you're ending up with ultimately a spec width builder that will actually end up passing that spec width with the arguments uh, into the spec width and return an actual spec itself. So it's the spec width library builder is specified. I think yeah, right here. Spec width the implementation. If you have arguments, it'll generate specs. So each one of these things that you're going to be building out into HSpec is going to end up taking a spec and then executing it essentially. But the way you write out your spec is where the genius of the beauty of the Haskell language kind of like comes into play. This will look straight up like normal Haskell code. For folks coming in from Ruby or Python and looking at this example, might be wondering what the big deal is. All this syntax are just function calls. They are not actually using anything of the sort of that you normally see with Ruby, where you have to specify some stuff with the Ruby model, or in Python, where you end up having to write some annotations on top of existing functions to get the kind of the same functionality. This is just a consequence of the grammar. So to write out the top level of our test suite, we use a describe. Describing is a top level kind of like, oh, why don't you just go ahead and describe the actual test suite? It's really not necessary, but it's actually kind of good practice to go ahead and use that. Once you do that, notice that every time we're using $ do, this is again, if you remember, this is essentially another convenient way of doing composition without introducing extra parentheses. It's actually getting rid of a layer of parentheses for you. And once we do that, we can actually go ahead and describe multiple tests into this. For the first test, we're going to just go ahead and use it. It is defining a test spec. We're saying, let's say that we're going to use the example that, we want to test that 1 plus 1 is always greater than 1. Okay, this is the example that's in the book. Um, this will do nothing more than essentially verify 1 plus 1 is greater than 1. Simple predicate. You provide your predicate on the left-hand side. You use an in operator called should be that will take in the predicate, and it will essentially provide a pass or fail based on the truth of the value in its comparison to what you put on the right-hand side of the should be operator. So this is our first test that we've actually written into this. Okay. If we try running this guy, and obviously you'll see that if we go ahead and do this, and to stack build or stack GHCI, it'll probably allow us to actually set it up. Let's see, there might be an error that I wrote. Hmm. First argument should be okay. 1 second. I think I'm gonna have to add a pair of parentheses here. Um, Interesting. Defaulting the following constraints to type integer. Oh, okay. Never mind. That's that is in the first argument should be 1 greater than 1, and a statement do block should be true. Second argument is okay. I see. It is saying that the fact that we're using 1 plus 1 there instead of just a simple uh, test you're getting from the greater than side. It doesn't it's not computing this as being an ordinal. It's actually computing it as being a numeric because of the fact that we're doing addition, um, which is kind of interesting that it doesn't actually recognize that. But there's one way of doing this. We can actually also, um, you know, pass in or do like a. There's other ways of actually handling that, but I'll take care of that in a bit. So this is our first test. As you can see, it's actually executing the way we're expecting it to. We're actually leveraging monadic actions, sequence monadic actions, as we specified when we explained the do syntax last week, to actually go and uh, deal with this format. When we're actually writing out things that are supposed to be in sequences. Um, One thing to note about should be, I think, is that bears mentioning here is if you look at the actual info on type of should be actually, you'll see that type of should be is actually nothing more than it takes a type A that should be both equal and showable, and it will actually then allow you to go in and write get a curried function that does the comparison of A and returns an expectation object that will then be thrown as part of the result bits. That's actually how the execution engine kind of works. Um, and what's interesting to note is this equality is embedded in the actual specs, the HSpec library. Um, it uses show for most people who haven't seen show. I don't know if I remember discussing this because we will be talking about show in other parts when we are talking about monads and functors and so forth. But show essentially is a type class that essentially allows you to take in a type and return a rendering of that type. So you could write essentially like, things that will ultimately be printed to the console using an override of the show type class. You have to write an instance to be more specific of the show type class in order for your things to be showable. And once that happens, you can then use the entire standard library of generic algorithms that are already dealing with showable objects to actually go and display your object. Um, and in this case, once this showable happens, it's then leverages that to display the object if, say, an assertion fails or not. So let's go ahead and add one more test just to kind of show what this is happening. Let's go and this time write, just a straight up example. Uh, there we go. 2 plus 2 is 4. Okay, and we do dollar sign here, and we do 2 plus 2 on the left-hand side. Do should be, and we do 4 on the right-hand side. Okay, let's go ahead and reload our addition class here, and you'll see the same warnings about the type defaults because of the things that need to be showable or not showable here. You don't have to really worry about those type defaults right now. We'll go and figure out later on when we displaying them what would be the right thing. But they're not going to actually affect the actual execution of the program. You'll see that both will actually pass. If we make a mistake and say 2 plus 2 should be 5, which is really dumb, but it's for simple sake. If you go in and try and reload this, obviously, you could then run this, and you'll see that you get a failure, and you'll tell you what the expectation, what you got is false. So here we can actually go in and change this so it actually makes it more accurate, and we got our test suite all passing. So this is kind of what HSpec is kind of in a nutshell. We're not going to really touch base more about this. Obviously, you can you could totally see how you could leverage this to write more larger tests. As you can see, it is a huge library with a bunch of stuff, so you can actually get pretty far with writing a specification that's using this approach. And if this is something that's comfortable and up your alley, this can actually get you pretty far with your unit testing or even certain levels of testing that's not quick check based. without going and reaching out to some other third-party library that's available for you. I'm going to pause here first and see if there are any questions.
I'm good.
Thank you. All right, cool. And nothing on the stream. So we're going good. All right. So whereas specification tests is kind of like what we're mostly familiar with and looks very, very in line with our standard unit testing approaches, property-based testing is a completely different beast. All right. And as I mentioned before, it was pioneered inside the Haskell programming language. To understand and see how property-based testing works, we need to first add QuickCheck as a dependency into our library. All right. To do that, we need to go and add QuickCheck. Literally, it's a one-liner to our Cabal file. So here we just do QuickCheck, and then let's go ahead and load this guy up and do a stack build so that we get our dependency going. It will recognize that it's there in our workspace because it's part of the core testing library, and we rebuilt our machine, so it's there. Okay. So now let's go ahead and create a different test here. Go ahead and say import test.QuickCheck here instead for the moment. And let's go and comment this guy out so we can create a different main, all right, for the time being. Um, yeah. Now, our new main is going to use a different, it's going to have the same kind of keyword, all right? And I will first show this to you so you could actually see this. Um, doing a stack build, GHCI first for a second. It's going to rebuild our project and leverage the fact that we haven't loaded test quick check. But I wanted to first show you, just like HSpec, that this is a fairly complete library with its own set of functions. But the one thing that it shares in common, which is why I comment about HSpec, is the fact that, oh, interesting. It does not look like it requires me to actually do this. It looks like they've actually merged this correctly with, so it actually is not part of the standard library for test quick check. Okay, cool. So I do not have to actually go and do this. And I can actually leverage this. All right. So let's first write our first library. Um, first property, if you will. And yeah, we don't even have to do this. We can actually do something nicely like this. So we do not need to do this. So this is pretty neat. I did not realize this when I read this earlier. One of the nice features that one of the nice features of QuickCheck is the fact that it actually integrates well with HSpec. They're both part of the top level testing library. And one thing that this means is you can actually leverage the same unit testing like syntax that we have for HSpec with your your quick check test to actually build this out. Let's see how this works, all right? Let's say that we want to actually write out a quick check test that always tests the property that x plus 1 is always greater than x, all right? Basically, the successor function. We're basically testing that the successor function works the way it's supposed to. So we could write x plus 1 is always greater than x, $do like we normally do with the specification-based test, but now we write the property syntax, which if you see here, property is actually defined as a prop that will actually create a property object for execution. This is what we're actually going to leverage. And what this does is this requires you to provide essentially a um, a predicate into the program that it can test against. Okay, so here again, we're going to use $sign because we don't want to leverage parentheses here. And we're going to pass in our test property that we're going to deal with. In this case, this predicate is going to be a lambda function that takes in an x and returns x plus 1. And we're checking to make sure that this lambda function that it's taking in is always greater than the x that we provide, which we are casting has an int, so we're only dealing with a set of integers, specifically 30. I think int is 32-bit integers. So now uh, we can actually go and test the system. One thing to note, and I think it's important to realize, is why we're doing the casting. Okay, so let's first see what happens what happens when we try to load this. You'll see here that by not constraining it, you're getting a type error, okay? Because you're seeing ambiguous types that are being actually loaded, all right, based on the ordinal to be solved. And then it gives you some different ways of dealing with it. So by doing this, you've actually gone through and uh, fixed the issues and compiled and reloaded it, all right? So now when we run this, we can actually see that what X does is what the property test does is it actually goes through and generates like 100 different random inputs. It makes sure that it's always, you know, uh, greater than, and it will, tell you that if it passed if you after running a certain number of tests. Um, what's being hidden is what are the inputs that it's actually generating. We don't necessarily know what those are. But, the default, and we didn't actually configure it. We are just leveraging the defaults of these values. But let's try an example of, what would happen if we actually, fail this test. Obviously, I'm gonna write a completely invalid test just to force a failure. But let's see what happens if we say x is greater than x minus 1. This is never true, but we wanna see what happens when this occurs, okay? So when we run this, it'll load, but when we run it, you're gonna see, whoa, wrong, wrong, wrong. Not what we want. Is x minus 1. Why? What did I do wrong there? Oh, that's right. That's right. Never mind. This is always true. We want to do x plus 2, not x minus 1. X plus 1 is greater than x plus 2, which is false. Here, sorry about the snafu, folks. Sometimes that, you know, writing stuff in real time, it occurs. Um, so let's say that we have this test here, which is always going to be false. Okay, it's going to just generate one random input of the test. It's not going to actually do. This is one of the nice features of QuickCheck. If you actually run this guy, um, you'll see that it's going to hit the first failure and actually exit. And the first failure here that you see here is the input that caused the failure. All right. And all you have to do now is to rerun this. Um, is you could run, you could generate, a different test, or in this case, this test is completely invalid. You can actually go in and say X, and this will, obviously generate this correctly. Um, This rerun use match dash x is always greater than x plus 2 is obviously just if in case that you have a failure that you want to rerun. But I just wanted to show you the failure that it ends up creating. So it defaults into 100 tests here. Let's create a different test that we can actually fix. Um, let's see. Uh, let's create a property that says let's create a property that we could fix. Let's see. Um, let's test our actual. Um, let's write a function is even always returns true on even numbers. All right, and let's go ahead and create $do and we need to make sure property $x is even x is um equals true. So we have to generate random numbers that if so I'm going to be writing something a little bit more complicated here. Um, see if there's a way of writing this property. Um, this might not be the right test that we need to write. Got it. Let's say that we are developing, this is a bad example actually. This is not a good example for a property-based test. A better example for a property-based test is given two lists of size A and B, their concatenation is size A plus B. Let me go ahead and write this way. Uh, is size A plus B. That will do. And let's go ahead and write the property that given function x and y, which you can do, by the way, if you recall, we can actually do x y equals x plus y. We'll generate a function that's a curried function that's of two lists here. Let's see here. So let's go ahead and say how do we figure out the length of a list again? That was, if I remember correctly, length. No, it was this is, hold on 1 second. Let me just do GHCI here. Wondering if the prelude just did not understand. Weird. All right. GHCI. It's because the prelude was not added. Prelude. Go ahead and rewrite this. Length x plus length y equals length x concatenated with y. Okay. So let's do this and build this up, write this, reload, addition. See here. Right. Let me go look at something here just quickly. It's because of the string breaking down the way it's expected to is wrong. I have to hide because this is a multi-line. Okay. And let's go ahead and reload. See this? And it's complaining about what now? It is ambiguous type arising from property A0. It could be either A or B. Okay, so we need to provide uh, constraints on these guys, saying that A and B are both lists. Do this. Okay. And let's also do this and provide y being an integer. Now, let's see this here. Okay, this is all good. Let's see this. Addition. There we go. So by restricting it, we're basically telling what the properties should be generated, and you can see that we're going to get these things. Now, QuickCheck actually doesn't require you needing to use uh, HSpec. I just kind of like, when I saw that, I wanted to check it out. You can actually do what I was going to show you and create your own QuickCheck properties. So let's say that we take the property that we had here, all right, this x1 greater than 1. What you could do is create a what's called a property function. This is a property that you are trying to test, okay? So let's say we're doing um, addition greater, okay, int bool, okay? And let's say that it is going to do, it's going to take an x, and we're going to essentially check to make sure it's greater than itself. Also check this, it doesn't really matter, but just some less than, something less than what it is. All right. Um, Once you have this property, what you could do is create a function that returns an, let's say, IO monad here, or if you wanted, you could use main itself, but we'll just make a function just because it'll be easier. And this function, all it does is it's going to go ahead and run QuickCheck, which is part of the QuickCheck library, and this will take in the function that we wanted to test against. And when this gets run, second, variable not in scope. Go ahead and write this guy. Second. Oh, always. Go ahead and print out. Let's go ahead and create our property again. Addition getter later returns an IO monad prop x equals x plus 1 x, and now we could go ahead and create a quick check function that calls quick check on our property. All right, let's go ahead and do this, and we have our stuff loaded, and now we see our error here. This is created in one argument, and oh yeah, sorry, my it's wrong here. This is int to bool. Okay. So when we tried running QuickCheck here, you'll see that QuickCheck actually goes and runs our tests the way we expect it to. Okay. Let's say that we create the wrong thing that we said before. This has, as I probably pointed out, it's going to generate the same falsified inputs, and it will fail on the first input of that QuickCheck hits that fails the test suite. These are all randomized things that you could actually go in and leverage, but it is important to be aware of. QuickCheck generates a bunch of random inputs, but we haven't actually talked about how it does this. To introduce this, we're going to have to introduce a class called arbitrary. It's a type class that's part of the QuickCheck library. Who its point is it's going to go in. It's actually a function that I'm going to show you called arbitrary. It's part of the QuickCheck library that takes in um, a a type A that adheres to the arbitrary type class, and it returns something called a generator type. Okay. Um, so for a given type, what you could do is you could define an instance of the arbitrary type class to allow it to create different instances of this type, and then that would ultimately be used to create a generator of that type that would then subsequently be used to uh, be leveraged by, say, calls like, say, sample, which allows us to take a, type that's showable, and it'll create a generator for that type and returns us an IO mode for that as well. Or we can use sample prime, which allows us to create a collection of those particular list of those types. Um, You may be wondering why the IO monad is necessary in this case, and that is because of the fact that since we are using a global resource, an IO device that behind the scenes is going to help generate some of our random information. Okay, it's taking in a random seed usually, and I don't think we currently have control of that when you are actually building up the things. Um, that seed value tends to be uh, um, used to actually create the seemingly random data. And that's why, since we're not passing in the seed, we are using IO to um, essentially return a different result each time. Uh, so that way it can actually use this global resource of random values that exist, these random seeds that are available for us to actually go in and generate seemingly random data. Um, when we cover the monad section next week, well, not next week, in a couple of weeks, this will become very apparent as to why we can actually leverage this. We can actually go and reach out to the, say, the host operating system to get our random seed information, and then, use that to actually go and generate our seed, our random data. But the important thing to note is the arbitrary type class as it points out, is a type class. So if we grab I instance on arbitrary, you'll see that this type class actually has a bunch of instances defined on it for various types. And specifically, you need to create two different type of functions. You need to create an arbitrary function, and you need to create a shrink function. I think the minimum is just arbitrary, because shrink can be generated from arbitrary. But that actually is leveraged then for your custom types to create different properties of those types, and you can actually use that then to actually go and build out your functions. Sorry, your generators, right? Um, to create generators, really they are monads. Okay, a generator is if you look at I on gen, you could see that gen is is a monad. um, well, it has instances defined for functors, applicatives, and monads, and this is what ultimately is related because it's lifting up these values that are creating into this world where you can actually then manipulate them and use them in various contexts. That's why it's a monadic action. To create a generator is as simple as essentially creating a monad. And if you recall, we can create a very basic monad by using the return statement. So you might have something that called trivial int, and this is from the book, that can generate ints. And what trivial int does is all it does is return one. And this here um, can be leveraged to actually create samples. Um, so if we do sample of trivial int, you could see that it'll generate some samples for us. Okay, because remember, sample just takes in a generator and it'll return IO monad, and we'll generate different collections of this for us. We could also pass this into sample prime and actually also generate, this kind of things. Um, Another thing that you could also do is, create cyclic groups. So another example of this is, let's say, group 3 will generate integers. Okay, well, 1 through 3. If you want 1 through 3, this was going to be some finite set. You can actually leverage, what we've talked about before, the elements function, which is nothing more than something that takes in a list A and creates a generator. We can actually define this as nothing more than elements 1 through. And this now allows us to leverage, when we go in and, reload this, we can actually go and leverage this into sample 1 through 3. Well, let's use sample prime to get a collection of this. 1 through 3 to create a random set of samples of um, the random finite set that we have. Okay. There are also other things that you can leverage for generators, things like choosing orders and things like this. I'm not going to bore you with all the different types of generators that you could write out. The one thing to note though is you can there are already a lot of predefines, like I said, about these arbitraries that you can leverage. They'll create generators for you, and that would ultimately mean that they can be used as inputs for creating these finite random collections that we use using the sampling functions that I showed you. So honestly, that's it for the overview of the QuickCheck library. I thought we'd have time to actually go through um, an example with the, but honestly, I think it's great for you guys to cover and look at the Morse code example that's available. And by all means, um, if you have questions and stuff, just post it in the YouTube comments, and I'll get back to you as quickly as I can. So that's it for this week. Next week we will cover monoids and semigroups and start our journey up to monads. And I hope to see you next time. I hope you all have a good evening.